Hello everyone, I'm Dr. Vilayat Khan. In this lecture on microprocessor systems and interfacing, I'll talk about different number-based systems and convergence between them. In particular, I'll discuss how to convert from a number given in decimal number systems to a number in other number-based systems, and similarly from conversion from other number-based systems to decimal system. And also some computer data formats will be discussed. These data formats are the most popular to store data in the computer memory. Let's start with number systems. Uh, in each number system, there is a set of digits to represent different numbers in that particular number system. For example, decimal number system is widely used in our daily lives. Decimal number system is also called base 10 number system. And the reason base 10 system, the base 10 is used is that there are 10 digits in decimal number system, and those digits are 0, 1, 2, 3 until 9. So 0 to 9 are the digits of decimal system, and these digits are used to represent any number in the decimal system. For example, if I say 5,936, then 5,936 is a number represented in the decimal system. 5 is a decimal digit, 9 is a decimal digit, 3 is a decimal digit, and 6 is a decimal digit. So it's a number that has been represented in the a decimal number system. So in decimal number system, there are 10 digits, so that's why we also call it base 10 system. Similarly, there is a binary number system. In the binary, there are two binary digits. One digit is 0 and the other is 1. So these two digits are the digits of the binary number system, and these are the binary digits, so they're also in short represented with bit, which means binary digit. So 0 and 1 are the two digits in binary system. So if a number is represented in the binary, then every digit in that number must be either 0 or 1. So no other digit can be included in a binary system. There is an other system, octal system, which includes 0 to 7. It's an base 8 system because there are 8 digits. Similarly, binary system is base 2 because there are 2 digits. In octal, there are 8 digits, 0 to 7. And another one is hexadecimal system, where we have 16 digits in total, and it's also called base 16 system. In hexadecimal, the digits of the decimal system are all included 0 to 9, and as we need more 6 digits, then as there are no further decimal digits to include in this hexadecimal, so after including all the 10 decimal digits in the hexadecimal system, the rest of digits are taken from the English letters. So the English letters A to F, these 6 letters are included to represent the next 6 digits of the hexadecimal system. So in hexadecimal system, we have 16 digits, 0 to 9, and then A to F are the digits of hexadecimal system. So any number that is represented in the hexadecimal system must include either of these digits. So if there is a number that is represented with some digits, then the convention is that include that number in the parentheses and then write the base of that system after the most parenthesis, the closing parenthesis. So that base would actually tell you the number system that that is used to represent that particular number. For example, if there is a number 0, 2, so 0, 2 is a number, and one cannot be sure if 0, 2 is represented in decimal system or if it is represented in octal or hexadecimal. But one is sure that this is not in the binary, because 0 is a binary digit, but 2 is not a binary digit. So 0, 2 can never be in the binary system, but one cannot be sure if it is in the decimal or octal or hexadecimal system. So writing a parenthesis writing the base number after the closing parenthesis is important. So that is the normal convention. There are some notations used called the positional notation to represent a number in powers or weights. There is a radix base number or number base point, which is also called the decimal point. Normally, this decimal point is used to represent floating point numbers or fractions. And there are weights for each digit in a particular number system. There is a weight for that particular digit, and that weight is dependent on the position of the digit. So for floating point numbers, there is a decimal point, and on the right side there is the fraction part, and on the left side of the decimal point is the whole part or the integer part. So to assign weights in the decimal system, for example, the position after the decimal point, the weight of that position is 10 raised to power minus 1 in the decimal system, and the first position on the left of the decimal point is 10 raised to power 0, and that is also called the units position. And the position after the unit position is the tenth position, which is the weight of that position is 10 raised to power 1. And then there is a 100th position, which is 10 raised to power 2, then 1000, 10 raised to power 3, and so on and so forth. These weights can be used to represent a number in the power form. For example, 132 is a decimal number, and this can be represented in this way. And to understand how to represent a decimal number like this, then we have to read this number as this is 132, but we can read it as 100s, 30 tens in this number, and 2 units. So that's why we call it 132. So there is 100 in this number, 30 tens in this number, and 2 units in this number. So 100 multiplied by 1, because we have 100, and 3 tens, so we multiplied this with 10, and 2 units, so 2 is multiplied with 1. So when we can just multiply these numbers and add them, and we will get 132 again. But we will continue on the other direction, and we can write this number in the powers form, where 100 can be written as 10 raised to power 2. So 1 multiplied by 10 raised to power 2, which is 100, and 3 into 10 raised to power 1, which is 10, and 2 into 10 raised to power 0, which is 1. So we have just written this number using the weights or the power in decimal system. Number systems, this weights and power can be written for other number systems as well. For example, if we have a binary number and with a decimal point, this is a binary number 110.101. So this is a binary number, 3 digits after the decimal, 3 digits on the left side of the decimal point. So first, to calculate or to get its numerical value, we have to write the powers of the binary system for these digits. So as we have 3 digits on the right side of the decimal point, 3 digits on the left hand side of the decimal point. So you would just write 6 powers, 3 for the right side of the decimal point, and 3 for the left side of the decimal point. For the right side, for the first position, the base is 2, and the exponent is -1, then -2, and this -3. And if there would be a 4th digit, then we would write 2 raised to power -4, and so on and so forth. For the positions on the left side of the decimal point, we begin with 2 raised to power 0, 2 raised to power 1, 2 raised to power 2. If it would be a number in a different number base system, then we would write that base here. But as we are talking about a number which is in the binary, we are using base 2. So 2 raised to power 0 is the power for the first position, 2 raised to power 1 for the second, 2 raised to power 2 for the third, and if there would be a 4, then we would write 2 raised to power 3 and 2 raised to power 4 and 2 raised to power 5 and so on and so forth. So just weight is calculated just by calculating these powers. 2 raised to power minus 3 is 1 over 2 raised to power 1 over 8. 2 raised to power minus 4 is 1 over 4. 2 raised to power minus 2 is 1 over 2. 2 raised to power 0 is simply 1. 2 raised to power 1 is 2. 2 raised to power 2 is 4. So these are the weights. Now the binary number is here, and we have calculated the weights for each position of the digit. So just multiply the corresponding weight with the corresponding digit. This is the weight for the position on the first position on the right of the decimal point. So just multiply this with the digit on the right side of the decimal point. And this is the weight for the next position. So it is multiplied with 0. This is multiplied with 1. Similarly, for the weights on the left hand side of the decimal point. So this is the weight for the first position multiplied with 0 because we have 0 at this position. 2 is multiplied with 1, 4 is multiplied with 1. And after multiplication, we get these numerical values. 4 with 1 is 4, 4 with 2 is 2, 1 is 0 is 0, 0.5 with 1 is 0.5, and this is multiplied with 0, so we get 0. This is multiplied with 1, so we get 0.125. After adding this value, we get 6.625. So this is the numerical value of this binary number. Remember that these weights are the same for every 6-digit binary number, where the 3 digits on the right hand side and 3 digits on the left hand side of the decimal point. The weights would be the same for that number, but the result can be different depending on the value of these digits. For example, here we have 1, so that is multiplied with 0, we get 0 here. But if it would be 1, then we would get 1 here because 1 is multiplied with 1. Similarly, 0.25 is multiplied with 0, so we get 0 here. But if this digit would be a 1, then we would get 0.25 here. So obviously that would change the value of this final numerical value. So that would be the numerical value for that different number. So remember that this is the binary number. We write power here, and then we calculate the weights and multiply those weights with the corresponding digit and add the result. So we get the numerical value. And this numerical value is in the decimal form. We can do the same treatment with a number represented in the base 6 system. Base 6 system is a system which has 6 digits, and the convention is to take the first 6 digit of the decimal system. And if we want to design a system, a number system with more than 10 digits, then take the first 10 digits from the decimal system and take letters from the English alphabet for the rest of the digits in that system. So this is base 6 system, so we have 0 to 5 digits, and this is the number 25.2. So we get the power 6 minus 1, 6 raised to power 0, 6 raised to power 1, and just calculate these powers, and we will get the weights for the corresponding position of the digit. And then multiply these weights with the corresponding digit. For example, 0.167 is multiplied with 2, so we get 0.333. 1 is multiplied with 5, we get 5. 6 is multiplied with 2, we get 12. Just add them and we would get 17.33, which is the numerical value of the number represented in the base 6 system. Conversion to decimal. We have already talked about conversion to decimal. In fact, when a number is given and when that number, a numerical value of that number is calculated, then the numerical values are in the decimal system. So this method of calculating the numerical value can be considered as conversion to decimal system. So we have just learned how to convert a number given in a particular base system to decimal system, and the method is to just write the weights, the number given as an input. For example, this number is in the base 8 system, 123.7. So just write the weight the power of the base 8 for these number of digits. We have a decimal point here, and we have just one digit on the right hand side of the decimal point. So just write 8 minus 1. Then for the left hand side, 8 raised to power 0, 8 raised to power 1, 8 raised to power 2. So these three weights are for the digits on the left hand side of the decimal point, and this weight is for the digit after the on the right hand side of the decimal point. If there would be more digits, then we would add more power here, and then from this power we can calculate the weights for each position. So these are the weights for the 4-digit number in base 8, and we can do the same for any other number with more digits after the decimal points or on the left hand side of the decimal point. So we just need to multiply these weights with the corresponding digit. These are the weights for the corresponding position, and we multiply these weights with the digit at that particular position and sum them. So after sum, we get 85.875. This is the value, the numerical value represented in decimal system. So this method, this is actually a conversion from a number given in the base 8 system to a number in the base 10 system. So we have just converted this value, which is in the base 8 system, to a value in the decimal system. Similarly, we can convert other numbers. For example, we have a number given in the binary system. So this is a number in the binary system which has 4 digits on the right side of the decimal point, and this number has 5 digits on the left hand side of the decimal point. So 4 plus 5 are the number of digits in this system. So we have 9 digits in this number, and we would just write the power in the binary system for these number of digits. So here is here are the power for these number of digits. So here we have the decimal point, and on the right hand side of the decimal point, the first power is 2 raised to power minus 1, minus 2, minus 3, and minus 4. And for the digits, we have 5 digits. So after on the left hand side of the decimal points, we just write 5 powers for these digits in the binary, which is base 2. So 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, 2 raised to power 3, 2 raised to power 4. So just calculate the weights of these power, which are these values, and multiply with the corresponding digits of the binary number. For example, this is the power, this is the weight for the 4th position on the right side of the decimal point. This is position 1, 2, 3, and 4. Multiply this weight with the digit on the 4th position of on the right side of the decimal point. And because this digit is on the 4th position, so multiply this with the weight on the calculated for the 4th position. So this is multiplied with 1, we get here. This is multiplied with 1, we get here. This is multiplied with this digit, we get here. 0.5 is multiplied with 0, so we get 0, and this is decimal point. And then for the digits on the left hand side, just continue the multiplication. 1 with 1, we get 1. 2 with 1, we get 2. 4 is multiplied with 0, so we get 4. 8 is multiplied with 1, we get 8. 16 is multiplied with 1, so we get 16. So we have to add these values, and we would get the numerical value for this binary number, which is 27.4375. So this numerical value is the equivalent number in decimal system, and in other words, we can say that we have just converted this binary number to a decimal number using our conversion method. So binary numbers can be converted to decimal, octal can be converted to decimal, and we have shown an example of converting a number in the base 6 system to a decimal system. And similarly, we can convert hexadecimal numbers to decimal as well, and the procedure is exactly the same. This is the number in hexadecimal system 6a.c. The dot is missing here, but that is there. 6a.c. This is a number given in the hexadecimal number system, and we have to convert this number into decimal system. So we have to calculate a number in decimal system which is equivalent in value to this number in hexadecimal. So just write the power 16 raised to power minus 1 for the digits on the right side of the decimal point, and For the left digits, 16 raised to power 0, 16 raised to power 1, because we have just two digits. Calculate the weights and then multiply it with corresponding position. Here we have the weight for the base 16 system is 0.0625. This is multiplied with C, and the value for C is the value for A is 10, the value for B is 11, the value for C is 12. So this is multiplied with 12. So after multiplication with 12, we get 0.75, and here we multiply this one with A. So A is equal to 10 because that represents the position 10, or that is the 10th digit. So we get 10 here, and this is a digit in decimal system. So we just multiply it 16 into 6, so we get 96. Add them and we get this value which is in the decimal system. So this method shows how to convert a number in the hexadecimal system to an equivalent number in the decimal system. So we have just seen few examples to convert numbers and different base systems to a number equal to decimal, a number in decimal system. So from any other number system, we can convert to decimal number systems. This is conversion from decimal number. So we have to convert a number given in decimal system to an equivalent number in any other number based system. So we have to separate the number into integer part and a fraction part. So the input number that we want to convert to other number system is given in the decimal number system. So a number in the decimal is given, and we have to convert it to a number in any other desired number based system. So for that to do, we have to write the number in and separate the number into integer part and fraction part. For example, this is the number 25.34, and then in this number 25 is the integer part and 0.34 is the fraction part. So we have to separate them and we have to convert each part independently, and then we have to combine together with the decimal point. So conversion from a decimal integer. If we have a number which is an floating point number with a decimal integer part and fraction part, so we have to just separate the integer part and convert that integer part. And a number can also be given which is just of integer part and doesn't include a fraction part. In both cases, we start conversion from a decimal integer, and we just first convert the integer part to the desired output number system. So divide by the radix or the number base. So divide the integer part of that number in the decimal system with the radix or the base of the number system that we want to convert to. For example, if we want to convert this 25 in decimal to binary, then divide this 25 with 2. If we want to convert this number into base 8, then divide this 25 at the 8, because that is the radix. So divide by the radix. Divide the decimal integer by the radix or the number base. This is the first step. Then in the second step, save the remainder. First remainder is least significant digit. Keep on saving the remainder. Each time you divide the integer decimal integer with the radix of the number we want to convert to, save the remainder. And each time the quotient we get the quotient, just repeat step 1 and 2 for the quotient until the quotient is 0. So continue the division on the remaining quotient and keep this process until we get a 0 as the quotient, and keep on saving the remainder. And remember that the first remainder is the least significant digit, and the second remainder is the next significant digit, and so on and so forth. So to understand this procedure, let me include an example to understand this procedure of converting a decimal number system to any other number system. So let's suppose we have to convert a number 10, which is given in the decimal system, to an equivalent number in the binary. So in the binary, we know that the base or the radix of the binary system is 2. So we have to divide the integer decimal with 2. 10 is integer, and we assume that there is no fraction point or decimal point, and if there would be a decimal point, then we would first convert the integer part of the decimal number by dividing with the base 2, and then we would convert the fraction part separately, and we will see example of the fraction part conversion. So we in this example we are going to convert 10 in the decimal to binary. So as the target system is binary system, which is base 2, so we have to divide this 10 with 2. So we divide 10 with 2 and we get the first quotient is 5 and the first remainder is 0, and this 0 would make the least significant bit on the left hand side of the decimal point. And then we continue, as this 5 is not a 0, so we would continue the division with the base 2, and we would get 2 as the next quotient, and we would get 1 as the next remainder, and 2 is not 0, so again, so we would continue with the division. We divide with 2, so we get 1 as the quotient, and the remainder is 0. 1 is again not a 0, so we would continue with the division. So 0 is the next quotient, and we get this remainder. So we eventually got the 0 quotient, so we stop the division, and here we get a list of the remainders, and the first remainder is the first digit on the left hand side of the decimal point if there is one, or if there is no decimal point, then this digit just makes the least significant bit. This makes the next least significant bit, this makes the next, and this makes the final or the most significant bit of the number. So 0, which is this 0, 1, which is this one, 0, which is this 0, and 1, which is here. So 1010 is the final binary number, and this is equivalent to the decimal 10 in the decimal system. Here we have another example where we have to convert this number in decimal system to a number in the base 8 or octal system. So here we have the radix or the base is 8, so we divide 10, which is the number in decimal system, with 8. We just divide this number with this 10 is divided with 8, so we get the first quotient is 1 and the remainder is 2. We continue the division, we get the quotient 0 and the remainder 1, so we stop here because we got the quotient 0. We continue this division until we get the quotient is 0. So this is the first digit on the left hand side of the decimal point, or in other words, this is the least significant digit of the number in base 8. So 2 is the least significant digit, and this is the next higher significant digit. So 1, 2 is the number in base 8 system. So we have converted 10, which is in the decimal system, to 1, 2 in the base 8 system. So 10 in the binary is equal to 1010. 10 in the base 8 system is equal to 1, 2. So these two values represent the same number, but they are in the different number system. So this is in the binary number system, this is in the octal system, and this 10 is in the decimal system. So we have represented 10 and 3 different number base systems. Similarly, we can take another example, 109, which is in the decimal system, and we can convert it to base 16. So just divide the number with the radix or the base of the number system. We want to convert the number 2. So here we want to convert this decimal number to hexadecimal, and the base or radix of the hexadecimal is 16. So we divide this number with 16. So we get the first quotient, which is 6, and the remainder is 13. And this 13 in the hexadecimal system is equal to D, just like A is equal to 10, B is equal to 11, C is equal to 12, and D is equal to 13. We continue this division, and eventually we get to 0 as the quotient, but the remainder is 6. And this again would represent the least significant digit of the target number. So D is the least significant digit in hexadecimal, 6 is the next higher digit in the hexadecimal. So 6D is a number given in the hexadecimal number base system, and this is equal to 109 in the decimal system. If we are talking about the decimal fraction point, decimal fraction part, then we can convert that decimal fraction part to any other number system by multiplication using the radix or number base of the target number system. So multiply the fraction part by the radix or number base of the target number base system. Save the whole number, whatever the whole number we get in step 1, just save them, just like we saved the remainder on the previous slides. We have to save the whole number. Position of the result, even if it is 0, we have to save it as a digit. We will this whole number would make the digit of the target number base system. And note that the first result is written immediately to the right of the radix point. So whatever we get, the first digit that we get, we write that first digit immediately after the decimal point, and if we get the second digit, then we write it as the second position of the after the decimal point, and so on and so forth. So we repeat step 1 and 2 until the fraction part is 0. To understand this procedure, let me explain a few examples to understand how to convert the decimal fraction part of the decimal number into the target number base system. So let's suppose we have a decimal fraction part that is equal to 0.125, and we have to convert it to binary. Then the base is 2 of the target number base system, and we just continue multiplication with this base, which is 2 in this example. So we multiply 0.125 with 2, we get 0.25. This is the whole number and this is the fraction part, and we save this whole number, which is digit 0 after the decimal point. And as this fraction part is not 0, so we continue with multiplication. We take this 0.25 here and we continue multiplication with base 2. We get 0.5, again we get 0 here, the whole digit is 0, so that is our next digit after the decimal point. And this is the fraction part after multiplication, which is again not 0, so we continue with the multiplication, and eventually we get 0 at the fraction point, and we get the next whole digit, which is 1. So digit 1 is the next digit after the decimal point. So after the decimal point, this is the decimal point, this 0 is this one, the next 0 is this one, and this one is the final digit that has been calculated. So we stop here because we get 0, and if there is a number which where we do not get 0 immediately or after a few multiplication, then normally we just can proceed with few multiplication, and then we stop. In some numbers we will never get the whole and the whole the non-zero fraction part here, so we cannot just continue with the multiplication forever, so we have to stop after some multiplication. So normally in this course we will stop after 3 multiplication, so we have to go until 3 digits after the decimal point, and then we would stop. Okay, so this is another example where 1.125 is converted to base 8 system. This 0.125 is given in the decimal system, and we have to convert it to base 8. So we have to multiply with base 8. So when we multiply with this, we get the whole digit is 1 and the fraction digit is 0. So we stop here and we just get the first digit, which is 1, and we write it like this. 0.1, this 0 is just written to make the decimal point visible. So after the decimal point we get just 1 digit, and that is 1. In this case we got 3 digits and we wrote them. And here is the another example where we have a big number 0.046875, and we want to convert this to base 16. So just multiply this with base 16, we get 0.75. This 0 is the whole digit which we save, and 0.75 is not a 0, so we continue multiplication with base 16. So 0.75 is multiplied with 16, we get 12.0. So this 12 is the whole digit, which is digit C in the hexadecimal system, and this 0 is the end of the calculation. So we stop multiplications, we got 2 digits 0C, and they are written like this: 0.0, which is the first digit that represent the digit immediately after the decimal point, and then the next digit is C. And if we would not get 0 here, then we would continue multiplication with date fraction part with base 16, and we would get the third digit, and so on and so forth. There are a number of data formats used in the computer. Data formats are used in the computer to store data. So we, as computer machines, are operating on data. So first we have to represent data in a format that can be stored in the computer, that can be manipulated by the computer, and for that we need some data formats, some codes. And one of the most popular codes used in the computer, and also we are using the most frequently used code used in the textbook, and in particular in this course, is the binary coded hexadecimal, or in short BCH. So here we have a binary coded hexadecimal table where we have 16 digits, the hexadecimal digit, and there is a 4-bit binary code for each hexadecimal digit. So 0 to 9 and then A to F, these are the hexadecimal digit, and each hexadecimal digit is represented with a 4-bit code, and that is 000 for the 0, and 001 for 1, 010 is for 2, and so on and so forth. And finally for F, the binary coded hexadecimal code is 1111. To understand this, or to remember this table, just convert these numbers to binary, and if it is the number we get after the conversion is less than 4-bit, then write write zeros on the left hand side of that number, and to make them a 4-bit number. For example, when 0 is converted to binary, you would get just 1 0. Just write 3 other zeros on the left hand side to make this number a 4-bit number. And if 4 is converted to binary, then we would get 1 0 0. So just write 1 0 on the left hand side of this number. So 0 1 0 0 is the binary code for hexadecimal digit 4. And we can continue this until 9, but after 9 we get English letters. So English letters can also be divided. Just assume 10 for A, 11 for B, 12 for C, 13 for D, 14 for E, 15 for F, and just divide them with or convert them to binary. And whatever we get here, we would get this table. So these are hexadecimal digits, and each digit is represented with a 4-bit code. So this is binary coded hexadecimal. These are hexadecimal digits, but they have been encoded as the binary code. So binary coded hexadecimal. So this is the BCH code. Here are some examples. For example, this is a binary hexadecimal number, a number given in a hexadecimal system. Each digit belongs to hexadecimal system 2AC. So just get the BCH code for 2, which is 0010, for 2 0010. So write the BCH code or hexadecimal code for 2, which is 0010, for A, which is 1010, for C, which is 110. So this is the binary representation of the hexadecimal using BCH code. So a number represented in the hexadecimal can directly be represented as the binary bits using this table. And similarly, we can, on the contrary, we can convert a number in the binary to hexadecimal code. So this is 10000111101.1110. So just group them as 4-bit. For this 100, write 8. So this is according to the BCH code. This is 8. This is 3, and this is D, and this is E. So 83D.E is a number represented in the hexadecimal system. So using binary code, one can write a sequence of binary bits using hexadecimal code, or an hexadecimal code can be converted to binary easily using this table. So there are other codes, and we will continue discussion on those formats in coming lectures, and we will discuss them in further detail. If there are questions or queries during this lecture, please note them, and you can ask those questions or queries during the online session.